Okay, in this video we're going to consider the correlational research design. So let's open up some data to look at. So what we're going to use this time is the jump height correlation dataset from the example datasets for JASP. So find where you saved that and open that up. Okay, so we've got two variables in this data set. So we're going to imagine that what we've done is we've collected data from a single group of individuals. We've collected their jump height using some method, and then we've also collected their leg power, perhaps using something like a Wingate test. So what we're interested in is what the relationship between these two variables is. For example, do those with higher leg power have greater jump height or vice versa? So, first of all, let's start off with our simple general linear model, our linear regression model, and then let's demonstrate how this is equivalent to what would typically be used for this kind of study design known as a correlation. So we're going to go to the regression module here and we're going to go down to linear regression. And there's a little clue here because as you can see, correlation already sits underneath this. Now, one thing I will note is when you're using JASP, there are two main options for the analyses you can do. You can do classical, which is what we call frequentist statistical inference, and there are also Bayesian options for it as well. For simplicity's sake, I'm going to just use the classical or the frequentist models here, because the Bayesian models, if you've watched the lectures, require you to consider setting what are known as priors on the variables or on the parameters, in your data set. So we're going to keep it simple for the moment. So let's open up our linear regression. Now, what we want to do is take one of our variables, so for example, leg power, and pop that into our dependent variable. Then what we want to do is take jump height and pop that in as a covariate. Now, you have two options here, covariates and factors, but all these are different kinds of predictors in our regression model. If data is scale or ordinal, then it can go into covariates, or if it is nominal, or indeed if it is ordinal, it can go into factors. Jump height is a ratio scale data, so we're going to pop it into covariates. Now, what we get in this simple output over here, and I'm not going to go too much into some of the other details in here except for to very quickly demonstrate to you that you can look at various diagnostic plots for the regression model. I won't be going into this in other videos just for sake of time. What we get is we get a model summary which provides us with an R value, an R squared value, an adjusted R squared, and a root mean squared error value for what is called the null model. So this would be the equivalent of saying we have no predictors, all we have is leg power. So this is almost equivalent to saying an intercept only model if you recall back to the one sample study design. We get an ANOVA table, which gives a clue again to the equivalence between general linear models and different kinds of statistical analyses, including the analysis of variance. And then we get down here what is called our regression table with our coefficients in it. So we're going to focus on this for the moment, although you'll see there are some equivalences across these tables. So we have a number of rows in here. We have, first of all, our null model, which, as I said, is our H0, our null hypothesis model, which just has an intercept in it. And so all the unstandardized coefficient is for this intercept-only model is essentially the mean of our leg power data, and then this is the standard error for it. And this t statistic is just as though we were conducting a one-sample test or an intercept-only model for that variable. What we're interested in, though, is the model which has included jump height in it. Now, what we have is, as you can see, we have an unstandardized coefficient, but we also have a standardized coefficient. Now, the unstandardized coefficient tells us for every 1 unit increase in jump height, how much does leg power increase? Now, obviously, jump height is measured in meters here, so a 1 meter increase in jump height would be equivalent to quite a large increase in power. So if we were interested in the slope itself, this is the slope parameter for jump height in our model, then we might want to rescale our units to be in something like meters, so it was a little bit, in centimeters, so it was easier to interpret. The intercept tells us at what point the model intersects with the y-axis at the point essentially when x is 0. So when jump height is 0, what would it predict power to be? And now this is obviously kind of an impossible value, but we can still get some useful information from this kind of model to look at the relationship between these variables, given the range of data that we have. What we're interested in here, though, is what's called the standardized coefficient. So in the standardized coefficient, what we do is we take jump height and we take leg power, and they are essentially divided by the standard deviation of of each of the variables so that they're expressed in standard deviation units. And what this essentially tells us is that for a one standard deviation unit increase in jump height, there is a 0.984 standard deviation unit increase in leg power. Now, this is essentially the value that from our regression model is equivalent to what would be called a Pearson's correlation coefficient, which was mentioned in the lecture. Let me demonstrate this to you now. So, if we go back into regression and go to correlation, then it brings us up a new box, and we can put in our two variables here, and it will calculate what's called Pearson's R for us. And as you can see, the Pearson's R is exactly equivalent to the standardized coefficient for jump height in our linear regression model. So you can see that there is this equivalence between the two. Now, I mentioned also, and I'm only going to show this for this example here, I won't do this for all of them, but we can also think about our non-parametric versions of the different tests that we use. So, if for example we did not meet assumptions of normality with this data, then what we could do is we could look at a non-parametric version of it. Now, the non-parametric version of correlation is known as Spearman's rho. Now, if we were to calculate the rank transformations of our two variables and fit our regression model to it, what we will find is that the standardized coefficient on the rank transformed data is equivalent to what the correlation coefficient is for Spearman's rho correlation. So let's quickly do that now. We can add computed columns to our data set in JASP by just clicking on the plus button here. So if we open this, and I'm going to add in rank jump height. I'm also going to click on this button here, which gives us a little box to use what's called R code. R, as I think I've mentioned before, is a program that I use for the typical for most of my statistical analysis. It's a coding language that allows you to have a lot more flexibility and do a lot of additional kinds of analyses in it. But JASP essentially uses that language in the background. So I'm going to click on that and click Create Column, and then I'm going to double click here, and it allows me to put in some R code. So I'm just going to write a function called rank, and then I'm going to, using these little backward ticks, specify that I want to calculate the rank on jump height, click on compute column, and it will do that for me. I'm going to do the same for leg power, and then calculate the ranks for leg power as well. Just get rid of that one because it doesn't like it when you call it the name that is the same as the function. There we go. So there we go, there's a little tip for you as well. So now we've got two new two new columns with our ranked transformed jump height and our ranked transformed leg power. So now, let's open up another linear regression box. This time, we're going to add the rank transformed variables into our model. And as we can see, we get a standardized coefficient of 0.992. If we go back in now and open up another correlation box and add in the rank transformed variables, what we see is that our Pearson's correlation on these is also 0.992. But if I take these out, and I pop the original data back in, and I select the Spearman's rho option, you see that it is also 0.992, because what it is doing automatically here is taking those variables, rank transforming them, and then calculating the correlation coefficient on that data. So you can see the equivalence between these kinds of models, and hopefully that lets you get a little bit of an intuition for them. Now, what I'm going to do is I'm going to get rid of the two that we've just done, and I'm going to also get rid of that. Let's have a very quick look at the regression box, just so you can see where you can identify some of the model checks for some of the assumptions. If we go down to plots, there are a variety of different plots that you can do for residuals. So for example, we could look at the histogram of the residuals to see whether or not they look like they are approximately normally distributed. And they don't look too bad here. We can also do what's called a QQ plot. Now a QQ plot has a perfect line on it where essentially on the x-axis, if our data came from a theoretically perfect normal distribution, this is how we would expect it to be distributed. And then if we take our standardized residuals, we can plot them against that. And in theory, if it was perfectly met that assumption perfectly, all the dots would fall along the center line. Now we can see there's a little bit of deviation here, but we've got a relatively small sample. Maybe if we had a larger sample, it wouldn't look too bad. But this is pretty good to be fair. So these are some of the checks that you can do on your data for linear regression models. Now, what I'm going to do is I'm going to very quickly close this and we're going to go back to the correlation. Because typically, if you're doing this kind of analysis, you won't necessarily go in and run the linear regression model. You might jump straight to doing a correlation. The point of showing you the two, though, is so that you can understand how they are indeed equivalent to one another. And you can get an intuition for how essentially these tests, these name tests like Pearson's R and Spearman's Rho, are just components of that general linear model. Now, let's say we wanted to just look at our Pearson's R correlation between the two. We get the strength of our correlation, which is 0.984, and as we know, a value of 1 would be a perfect positive correlation, so we know that's a pretty strong correlation. Again, we get a p-value, and this p-value in this case is just testing to see whether or not we have a correlation that differs from the null hypothesis of 0. So what it says is if we assume that the null hypothesis is true, that is to say there's no correlation between these two, then what's the probability that we would observe the data we have seen, or even more extreme data? So if there really was no correlation, how likely would it be that we actually see this correlation that we've seen in the data here? And you can see that's very, very low, so that suggests that the data, that there may be indeed a true correlation here. Now, you can check some assumptions in here as well, so you can check, for example, things like multivariate normality of your tests. But what we really want to look at here is making some plots to enable us to visualize the data. So we have our statistic, but we want to also be able to look at the data. So we can make scatter plots for our data. We can add in, for example, distributions of our two variables alongside that scatter plot. We can even add the statistics onto the plot, so that when we include it in a results section, we can make that look nice and clear. We can also include what are known as confidence intervals on our plot, which give us the precision of our estimate of that relationship. And we can indeed also include prediction intervals, which come from our regression model, which tell us over what sort of range we would expect future data to be predicted to lie. So we can plot all of these various things and we can get a nice visual demonstration alongside our statistical analysis of the study design that we've conducted to look at this correlation between these variables. Hopefully this video has been nice and clear to show you how to conduct these and also to demonstrate to you that equivalence between the general linear model and the correlation that you might look at between two variables.